Thank you, Paul, for the introduction, and thank you for organizing this workshop. I really enjoyed listening to a wide range of interesting topics. In this presentation, I will talk about the project I worked on with Hinka Osinga, Claire Pottswaite, and Alistair Rockledge during my time in Auckland before coming to Cork. And at the end of the talk, I will sketch some ideas that I have been working on with Sebastian Rhetoric on spatiotemporal tipping. All right, so we're particularly interested in the cyclic competition or non-hierarchical competition between different populations. A very simple example of this kind of interaction is the classic children game of rock, paper, scissors. Scissors cut paper, paper covers rock, and rock smashes scissors. This kind of competition also has been observed in ecological examples. Particularly, there's a special kind of lizard called the side-blotched lizard. And the males of this lizard come in 3 different morphs of color: orange, blue, and yellow. Each of which has a very interesting or very unique mating strategy. The orange males are aggressive and territorial, which gives them sort of a huge advantage over the blues. Their weakness, however, is that they're polygamous, which means that they easily lose track of their female partners. This gives the chance for the yellows or the sneakers to sneak in and mate with the females in the orange territories. Now, this might strike you as a very clever strategy of the yellows, but it's not really effective against the blues, because the blues, the blue males are romantic, they're faithful, and very protective of their partners. So to sum up, orange will beat blue, blue beats yellow, and yellow beats orange. So we're interested in the sort of phenomenological aspects of such cyclic interaction in spatially extended systems. And we consider this a conceptual model, which is a system of PDEs in a reaction diffusion form. The state variables A, B, and C represent the densities of the 3 competing populations. We have zeta and sigma as constant parameters. We're going to fix sigma for now and use zeta as a varying parameter that corresponds or sort of describes the aggression rate between competing populations. The left-hand side here is the derivative with respect to time, and the Laplace operator models the mobility across the spatial domain, which is parameterized by the independent variable x. So here I'm showing an example of how the distribution of the populations A, B, and C vary across the one-dimensional domain. I'm plotting the populations in the logarithmic scale, and you can see that the populations try to invade each other in a form of waves. So for example, red invades blue, blue invades green, and green invades red. Right, so this is an example of a stable traveling wave where the ecosystem is sort of sustainable, right? Now, because there are many degrees of freedom in the PDEs, instabilities of traveling waves may manifest themselves in numerous ways. But the main mechanism that we find in our system is the following. The amplitudes of the waves oscillate in time and eventually pave the way for steady state solutions where each population is distributed evenly across the domain. So you can see the amplitude here oscillate in time, and in the long term, you will see that the ecosystem sort of collapses and only one of the species will survive at a given point in time. All right, so this is another way to look at it. So if we plot the amplitude of the waves as a function of time, you can see the state of the system will tip from this sort of periodic behavior and eventually goes to a steady state where only one of the species survive. Okay, now in order to understand this instability mechanism, we perform stability analysis for the traveling wave solutions. In particular, we saw for this augmented eigenvalue problem. I won't go through the details of this for the interest of time, but you can reach out for me after the talk if you want to know. However, I will say this. If you have a system of ODEs, right, then the stability of a steady state or a periodic state is determined by sort of a finite number or counted number of eigenvalues in the linearized system. On the other hand, PDEs is regarded, the system of PDEs are regarded as infinite dimensional systems. So each traveling wave solution is associated with a continuous spectrum of eigenvalues. Here I'm showing 3 examples of such spectrum by fixing the aggression rate zeta and varying the wavelength L. Right? So if the spectrum does not extend to the positive half of the complex plane, as you can see in this case, then the corresponding traveling wave is stable. If it does extend to the positive half plane, then the corresponding traveling wave is unstable. The transition between the two occurs through what we call an Eckhouse bifurcation, where the curvature of the spectrum changes sign at the origin. Once this bifurcation is detected, we can sort of continue it as a one-dimensional curve in 2-parameter plane. So the orange curve here is the Eckhouse curve, and it divides the 2-parameter plane into a stable region and an unstable region. And in the context of tipping, if we, for example, increase zeta monotonically and move from the stable region to the unstable region, we encounter what we call a bifurcation-induced tipping, as we have seen in a number of talks in the past 2 days. On the other hand, if we encounter sort of a non-monotonic change in zeta, where we move back and forth between the 2 regions, then we will have the following situation. So when the rate of the environmental change exceeds some sort of certain threshold, the ecosystem will collapse and we encounter a rate-induced tipping. And the critical rate of the environmental change or the position of the threshold depends on the wavelength of the traveling wave.
2 minutes left, Chris.
Yep. And this threshold also depends on other factors, such as the speed at which the populations move and the magnitude and the nature of the environmental change. So at the moment, I'm working with Sebastian on extending the existing framework of tipping points and try to develop methods for investigating tipping points in conceptual PDE models, as well as spatially extended systems. And I think this is a good place to stop. So thank you for your attention.